mentioned, I'm Jamie Thompson, a principal mathematical modeler here at DNV. And today I'm going to give a short presentation discussing the safety analysis of hydrogen refueling stations. In particular, I'll be focusing on how using advanced computational fluid dynamics, or CFD tools, can help to support the assessment of suitable safety or setback distances for such facilities. Okay. Now on this slide is a brief overview of the structure of today's talk. Now, hydrogen has been identified, as we know, as an essential element in the energy transition, and it has a crucial role to play, we believe, in the transport sector moving forward. Now, the demand for alternative fuels continues to grow, and hydrogen is an attractive option due, as we know, to its high energy content, zero emissions at the point of use, and also its potential for renewable production. As we continue to embrace hydrogen as a fuel, the need for hydrogen refueling stations, of course, becomes increasingly crucial. And according to a report by the International Energy Agency, the IEA, the number of refueling stations worldwide more than tripled in the period between 2016 and 2021, rising from around 200 to just over 700 in that window. Now, while hydrogen is a promising alternative to fossil fuels, it is, of course, not without risks. And as with any fuel, proper handling and storage are necessary to ensure safety. Indeed, conceptually, a hydrogen refueling station is not all that different from the commonly seen LPG or natural gas facilities. Hydrogen is stored, after all, like any fuel, in pressurized tanks on site and delivered to vehicles via dispensers on demand. However, hydrogen also has some unique characteristics that require special consideration. So before we move on, let's just take a moment to talk through what these are. First, and perhaps most notoriously, hydrogen has a very large flammable range. The gas is flammable in air at concentrations from as low as 4% up to 75% by volume. And this contrasts starkly with the flammable range for methane, which is in the 5 to 15% range. Hydrogen is also really light, around 8 times lighter than methane. And this, of course, is an advantageous property, as it means that in many circumstances, there is greater potential for hydrogen releases to drift out of harm's way following an accidental release. Whilst hydrogen has a relatively low energy density by volume, it must be stored at high pressures in order for useful vehicle ranges to be achieved. So there's that safety aspect to consider as well. Furthermore, hydrogen has a low ignition energy, and it's therefore far more readily ignited than other fuel gases. Compounding this, the material has associated with it a negative Joule-Thomson coefficient, which means that it actually warms up as it expands at the typical usage temperatures, leading to an increased propensity for spontaneous ignition. And finally, in sufficient concentrations, hydrogen burns with a very high flame speed and has significantly greater potential to undergo a deflagration to detonation transition that can see pressures as high as 20 bar. Now, given the high buoyancy of hydrogen, as we've just mentioned, and its comparatively high potential to self-ignite, I just want to emphasize here that this does not mean that explosion risk can be ignored. Now, whilst it's true that the gas will naturally rise when unconfined, a leak from a component of a hydrogen refueling system will typically occur at very high pressures. By necessity, because we talked about this low energy density, needs to be stored at high pressures to be useful to us. Here, the momentum of the jet will actually dominate the flow initially, creating the potential for large flammable clouds to form at low levels before the gas has an opportunity to rise, before buoyant forces become significant in the overall dispersion behavior. The buoyant nature of the gas can actually also take a backseat in terms of cloud development, at least in windy conditions. And we'll see a little bit of an example of that a little later. Secondly, whilst the gas has the propensity to self-ignite, and this is accepted, it is far from certain that this will occur. And a clear example of the explosion risk for hydrogen leaks, where gas was able to accumulate in significant quantities before finding an ignition source, is the Cherbourg refueling station incident in Norway from a few years ago, where a very large explosion occurred following a leak and leading to heavy damage to the facility. There were fortunately no fatalities associated with that event. Next slide. Okay. Now, as indicated earlier, hydrogen, like any other fuel, carries risk, and this must be managed to allow it to be used safely in the transport sector, or indeed any other sector for that matter. For hydrogen fueling stations, which tend to be located in populated urban areas, where they are, of course, most useful, a key safety measure is the establishment of appropriate safety or setback distances, as they're sometimes called. Now, a safety or setback distance in this context is simply defined as the minimum separation distance between equipment in hydrogen service and an exposure group, for example, people, buildings, and indeed other neighboring equipment. So it's the minimum distance that's needed to reduce risk to these groups to an acceptable level. We should note here that the safety distance is in fact a two-way measure and must also account for external hazards presented to the hydrogen system itself. A vehicle fire in a neighboring parking spot could be an example here. Now, a range of codes and standards have been developed to assist with the design of hydrogen refueling stations, including guidance relating to the establishment of appropriate safety distances. Examples include the NFPA, National Fire Protection Association, IGA, the European Industrial Gases Association, and ISO, the International Organization for Standardization. There are several others. I mean, there's a British standard, for example, as well. And whilst the guidance provided by the various codes and standards has a similar goal, the safety distances obtained can actually vary significantly due to differences in approach between them. In general, though, at a high level, at least, the nature of the assessment will fall into one of the following categories. Designed by code, where a listing of safety distances will tend to be provided that can be directly applied, or perhaps at most with some interpolation between line sizes and pressures, etc. There's the deterministic or consequence-based assessment, perhaps based on a specified representative release. And then finally, there are risk-informed assessments, where both frequency of occurrence and consequences are taken into account. In most cases, designing to code has the advantage that there is no need to perform detailed modeling, as distances for different line sizes and pressures, etc., are predefined within the code itself. An additional advantage is that justification of any proposed site layout is therefore relatively straightforward. You need to simply follow the code and then reference that this has been done. The downside, though, is that designing to code involves using safety distances that are generic and therefore, by necessity, can be conservative, as they don't reflect the specific characteristics of the particular system that you're looking to install, to design and install. And this can be problematic for a number of different ways. For example, if site space is limited, and that could be a situation, or quite a common situation, in fact, where the hydrogen refueling system is being retrofitted into, say, an existing gas or petrol station. It's common to see designs where a number of parking spaces within an existing gas or petrol station are occupied by the hydrogen refueling equipment, the compressors, and so on. Now, if designing to code proves to be problematic, or if it's simply not an option in the country or region where the installation is planned, the alternatives are generally the risk-based or consequence-based assessments I mentioned earlier. In either case, it will be necessary to perform consequence modeling to support these assessments. And typically, this will involve assessment of flammable gas dispersion distances, jet fires, and gas explosions. Now, these assessments can be supported by a broad range of tools, enabling the calculations and assessments to be performed to different levels of detail as required. Often, a pragmatic approach here is to select integral or semi-empirical models, which are quick running, such as those provided by FAST. However, whilst these models are extremely useful and will often form the foundation of such assessments, there are circumstances wherein they may need to be supported or entirely replaced, in fact, by more advanced CFD calculations. For example, CFD modeling may be required where geometry is expected to have a significant impact on the release due to, for example, impingement on neighboring equipment or firewalls. Another good example is where explosion risk for such facilities is to be assessed. It can be really difficult to judge what the appropriate cloud size and explosion strength is for these scenarios. CFD models come into their own here too, as they make it possible to explicitly model the development and ultimately consequences of representative releases, usually a subset. Now, for the remainder of the presentation, I'm going to talk a little bit about how the CFD tools KFX and EXSIM can be used to support assessments in such circumstances. I'll discuss some of the validation work that's been performed, focusing on the significant improvements that have been made in the field of hydrogen explosion modeling within EXSIM as part of our hydrogen JIP. And I'll include a comparison of the code's predictions with the results of a full-scale mock-up of a refueling station. Okay, so this is where the animations start and things potentially online could go a bit wrong, but let's cross our fingers and hope this works. Okay, so for the purposes of the presentation, is it working? Please work. Yes. Okay, I'd like to introduce a simple mock-up of a potential refueling station layout. Now, the model is relatively light in terms of detail, but contains many of the key characteristic components of such a facility. And the proposed setup is at least plausible, certainly sufficient to support today's discussion. To the right, as we look at it, or the bottom right, is the publicly accessible refueling area where the dispensers are located. This area, as we can see, is provided with a canopy to protect users from the elements. Behind the dispenser area is the main equipment compound that contains the majority of the site's equipment in hydrogen service. Here we have storage to the far left, the compression system in the center, and there's a chiller to the right that's partially obscured by the canopy. Finally, on the far left is the tube trailer enclosure and the tube trailer. So this particular facility relies on hydrogen being distributed, provided by road, rather than generating it on site, which of course is another design variant that's perfectly viable. The solid blue separating walls here are representative of firewalls, whilst the semi-transparent areas represent fencing. They're porous regions in the model. And these, unlike the firewalls, are simply designed to prevent unauthorized access to the compound, but they don't serve any other particular safety function. Now, the accidents of primary concern at hydrogen refueling stations do, of course, tend to begin with an accidental loss of containment, perhaps due to a leakage from a fitting or even part of the system suffering physical damage. Whilst we do, of course, need to manage risk throughout the entirety of the site, we are particularly concerned always with the publicly accessible dispenser area. And as you would expect, tolerance of risk in such an area is always lowest. For our demonstration, let's consider a 1 kilogram per second release directed towards the dispensing area, indicated here by the red arrow. We have a firewall segregating these two areas, so we expect to have significant protection from the effects of fire and, to some degree at least, flammable gas dispersion. It's the dispersion and ultimately the split explosion risk that we're going to be focusing on for this demonstration. Okay, so let's begin by exploring the hazard, considering relatively calm conditions. So a 1 meter per second wind or light breeze, as it is really, directed towards the dispensing area. Here we can see that the horizontally directed hydrogen jet impacts quickly on the firewall and is subsequently dispersed around the equipment compound, rapidly forming a large flammable cloud in this area. However, due to the combination of the light wind and the buoyancy of hydrogen, after that initial momentum is knocked out by the impact of the gas jet with the firewall, the resulting plume begins to rise and there are no signs of ingress into the dispenser area. So here, the firewall is doing an excellent job of screening this area from the release. The yellow kind of semi-transparent cloud that you see developing there is what we call an ISO surface at 4%. So basically what we're saying is within that region, there's a flammable cloud of a flammable hydrogen air mixture. Okay, so low wind conditions, we see that our dispenser area is safe, certainly from flammable gas dispersion. Let's now rerun the simulation, but with a slightly higher wind speed that is often used as one of the representative speeds in safety studies, so 2 meters per second. Again, we see the equipment compound being flooded with gas, and well, there isn't much we can do about that after all. But now we are beginning to see the hydrogen plume drifting in the direction of the dispenser area and beginning to accumulate, to some degree at least, under the canopy. So we haven't yet got a large explosion cloud in the flammable cloud in the publicly accessible area, but you can see how the impact of the increased wind speed is being manifested. Finally, here is a third case with the other most commonly considered wind speed, 5 meters per second. And here we can see that the combination of the recirculation region, this low pressure region behind the firewall, and the relatively high wind speed gives the plume very little opportunity to rise in the early stages of the release. And as a result, significant quantities of flammable gas are starting to accumulate in the dispenser area, and most troublingly, at low levels. And on this next slide, you can actually see that in the image to the right of the slide, you can see that the plume is actually touching ground level in flammable concentrations for this wind speed. So what have we learned from these simple simulations, and where can leveraging CFD methods help us go next? Well, we have seen that whilst firewalls are known to provide excellent protection against the hazards presented by early ignition of accidental releases, culminating in jet fires, they're not anywhere near as effective at containing flammable gas plumes, even when the released gas is extremely buoyant, such as the case we have here with hydrogen. This means that we can't necessarily apply a simple cutoff to our hazard range calculations for flammable gas in the same way that we might, albeit not always correctly, for fire hazards. Now, we could, of course, say, okay, in this case, we'll simply use integral models to calculate the dispersion distance. We won't apply a cutoff. We'll simply use integral models and set our safety distances based on those results. However, such calculations don't actually take into account the influence of the geometry. And if you do that, you can end up with extremely conservative results, and perhaps it will make a design for your particular site impossible. CFD here can also be used to explore how adjusting the layout could potentially reduce the risk. It was clear, for example, that moving the dispenser area a matter of meters away from the compound could greatly reduce the hazards at these higher wind speeds. Again, referring to the image on the right, just a matter of meters, you can see that you could move the publicly accessible area outside the flammable plume, and that can make a big difference. We can also explore the impact of changes in firewall height and design. The list goes on. And I touched on it a little earlier, but the other really useful output from these dispersion calculations is an indication of the size and location of the flammable clouds that are formed. And this is a critical input for explosion calculations. Now, as shown by the Sherbo incident I referenced earlier, explosions present a very real hazard at hydrogen refueling stations. And it's therefore critical that they are adequately treated in any safety assessment for these facilities. We've already seen how CFD simulations using KFX can help us understand the gas dispersion and accumulation behavior at these facilities. But how do we then begin modeling the consequences of the resulting explosion? Well, guidance is available for selection of explosion strength using approaches such as the TNO multi-energy model, which is available in FAST. But these methods are really suited to congested plant and also for making predictions in the far field. And it can be really difficult to know what the appropriate selection of explosion strength should be when you've got a layout such as we have for a hydrogen refueling station. And CFD can provide the answer here too. I've already accidentally run the simulation, the animations, but we'll do it again. So using the same facility, here is a simple simulation of a hydrogen air explosion occurring following delayed ignition of an accidental release within the main equipment compound just behind the refueling area where the dispensers are. The calculations were performed using EXSIM, which is a gas explosion simulation code and part of the overall KFX suite. Here, we've simply used the same geometry and run the calculations in the EXSIM code. And as we're modeling the explosion using EXSIM, we don't have the headache I just discussed of trying to select an appropriate explosion strength. The code itself models the developing explosion and predicts the generated overpressures based on the details of the local congestion and confinement. So I'll just run those again when I continue. Okay. Now, the one caveat here, though, is that you do need to make sure that the geometry is adequately represented in your model. Now, as the predictions are highly sensitive to this. In fact, it's the detail of the geometry that dictates the outcome of the simulation in terms of explosion overpressures. And generally, we recommend modeling down to items or piping around an inch or so in diameter. Now, whilst suitable for dispersion simulations, the level of detail in this simple mock-up can be seen to be, based on what I've just said, a little low in truth for explosion analysis. And fortunately, though, CAD models are generally available for new projects, and KFX and EXSIM are able to import CAD models in a variety of formats. They can be, the highly detailed models can be imported directly into the codes. Now, of course, you can't rely on the predictions made by these tools without sufficient validation. KFX has been extensively validated against a broad range of materials, including hydrogen. And for EXSIM, we've recently undertaken a major validation effort for hydrogen explosions, and an improved version of the code is being released a little later this month. The validation work is ongoing. Before I sign off, let's just take a quick look at a particularly relevant validation case that we are actively working on. Now, I should stress that these are provisional results, though we believe that they are sufficiently representative of the model's performance and unlikely to change much between now and when they are published in the model's validation summary document. So the basic setup is a simplified representation of a hydrogen refueling station with a boxy car, a couple of dispensers, and a firewall. The whole area was flooded with a slightly rich hydrogen air mixture, and the extent of the cloud is indicated by the semi-transparent box, which is bounded by the steel framing that surrounds the overall experimental rig. Pressure transducers were positioned in various locations, including at the wall, and you can't see them, but underneath the vehicle. And finally, the hydrogen air mixture was ignited between the two dispensers, and as indicated by the almost visible lightning strike symbol that you can see there. So let's take a look at the results. On the left, we have a plot of the experimentally measured pressures against EXSIM's predictions. So the x-axis is the experimentally measured value, and the y-axis is the predicted value. Now here, a perfect prediction would land on the solid line running from corner to corner, whilst predictions landing within a factor of 2 of the experimentally observed value lie within the band bounded by the 2 dashed lines. On the right is what we call an MV plot, which is a plot of geometric mean bias against geometric variance. And this essentially gives us a feel for the uncertainty in the code's predictions. And here, a perfect prediction would rest at the bottom of the parabola that defines the minimum achievable variance. Now, as can be seen, EXSIM overall does a good job, a really good job actually, for an explosion code of predicting blast overpressures across the range of measurement points found in this experiment. And here the code, we can see, predicts the experimental value to within a factor of 2, approximately 71% of the time, showing a slight tendency to overpredict. Overall, a very satisfying outcome. Right. To summarize then, if hydrogen is to meet its potential for helping to decarbonize the transport sector, it's crucial that we have a sufficiently large network of hydrogen refueling stations. Hydrogen, like any other fuel, is hazardous. We recognize that, and we must pay attention to its unique characteristics if we're going to operate this growing network of facilities safely. A key component in such safe operation is the establishment of suitable safety or setback distances. And as we've seen and discussed briefly, several codes and standards have been developed to help with this. Adoption does vary from region to region, so the nature of the allowable designs might vary as well in a similar way. If the facility is not to be designed to code, consequence modeling will generally be needed to support the analysis and the safety documentation. And as we've seen, well-validated CFD codes can provide really valuable insights, especially where geometric effects play an important role in determining the hazard ranges.